Welcome. In this video we're going to be exploring questions relating to the OCR GCSE Computer Science Spec exam questions on data representation. And to get us started, we'll look at questions on units and binary numbers. When we're talking about units, we're talking about how we're collecting and measuring values held inside a computer. As hopefully we're aware, the unit of measurement inside a computer is a binary digit. So that would be either a 0 or a 1. And we collect all these zeros and ones together to hold information. A single 0 or 1 is known as a bit. If we have 8 zeros and ones together, so 8 bits, we refer to that as a byte. B-Y-T-E. If we have 1,000 bytes, referred to as a kilobyte, 1,000,000 bytes, a megabyte, 1,000,000,000 bytes, a gigabyte, and 1,000,000,000,000 bytes, a terabyte. You don't need to learn about petabytes, yottabytes, zettabytes, etc. I have missed one out though, which is that 4 bits, so that would be half a byte, is what's referred to as a nibble. Never let it be known that computer scientists don't have a sense of humor. What you've been asked to do here is to place in order these different values. What we're going to be looking at is the different attachment at the beginning here and what it means. And actually we are including a petabyte, so the P at the beginning here means for peta, and the capital B is a byte. So that's a peta worth of bytes. And what's a petabyte? A petabyte in this context is 1,000 terabytes, and 1,000 terabytes is a gigabyte. 1,000 gigabytes is a terabyte. 1,000 megabytes is a gigabyte. It can get a bit confusing, but what we need to do right now is identify the right order. So let's go from the beginning, which is the smallest. So we'd say that the smallest in this question here would be a bit, because that's a single 1 or 0. So we start with a bit, and then we're going to go to a nibble, because the nibble was 4 bits. The next one along, can you see, will be a byte, because that's your 8 bits put together. And from now on, this capital B in front of this one and this one and this one means it's a certain number of bytes. Now the next one you normally think about is a KB, a kilobyte, 1,000 bytes, and that doesn't appear in the list. After that, it's 1,000,000 bytes, otherwise known as a megabyte, and that one is MB for megabytes. Then 1,000,000,000 bytes or 1,000 megabytes is referred to as a gigabyte. So the next one will be GB for gigabyte. The next one would be a terabyte, so 1,000 gigabytes, known as a TB, not in this list. And then finally, a 1,000 terabytes is what's known as a petabyte, so that's PB. In a question like this, it's simply asking you to convert from our number system of 191 into an 8-bit binary number here. Now, the straightforward way to do this is to write down the unit but in binary. So I'm going to write them in red. Start from right to left. You're going to start with 1. Because it's base 2, every single time you go to the left, you times by 2. So 2 1s are 2, 2 2s are 4, 8. You see what's happening? I'm simply doubling as I'm going along. Because it's a 8-bit binary number, I'm going to need to have 8 bits here. So 32, 64, and then finally 128. So that are the units for 128. Sorry, for an 8-bit number. And now I need to put 191 into this number. How do you do that? Well, you start on the left-hand side and you say, does 128 fit into 191? And the answer would be yes, you can fit 128 into 191. Now I want you to imagine now that you can sort of pour some of those numbers away because you've sort of allocated them, and then you've got 191, take away 128 because that's how much you stored. 191 take away 128 is, I believe that's 63. And then you continue with the process and you'd say, can you fit 64 into 63? And the answer would be no. So in this context, you write down a 0 because you can't store it. Can you fit 32 into 63? Yes, you can. Do you remember what you need to do now? Because you've actually stored those values, you need to account for it, and then we'll go 63, take away 32, because now you've stored some of those values, leaving you with 31. And then for the next one, you've got to ask the question here, does 16 fit into 31? Answer yes again, so you'd write down 1. Again, you have to account for the fact it's been taken away. Go you 31, take away 16, and that's going to leave you with 15. Can you fit 8 into 15? Yes, you can. So you write down a 1. 15 take away 8, because you have to account for the fact that you've now stored that. That's going to leave you with 7. And for the last bit here, 4. Does that go into 7? Yes. You now need to account for that. So 7 take away 4, leaving you with 3. Can 2 fit into 3? Yes. 3 take away 2, leaving you with 1. And then finally the 1 there. Great. Let's look at the next question. In the next question, it's asking you about converting this hexadecimal number of 3e into a decimal number. Now again, we want to do the same thing we did last time. We want to do the units. Now in binary, it's base 2, so you start with a 1 and times by 2 every time. In hexadecimal, it's what's called base 16. So you'd write down the units starting with 1, and then the next unit would be, because it's base 16, is 16 lots of that. So it would actually be the number 16. Great. Underneath here, maybe it's worth saying, the next one along would be 16 16s, or be 256. You won't generally need to have to know that or do that, but it's worth, well, it's a bit of additional information. Underneath 16, we can see that there's 3 of them, so we'd write the number 3 here. Under 1, we can see it would be E, so you'd write an E down here, see, because that's the number we're dealing with. Now, what is the number E? Well, E isn't a number, E is a letter. Why are we doing that? Well, as a quick recap, in hexadecimal, because that's base 16, we need 16 different values. So what we do is we go from 0 down to 9, but because it's base 16, we also need 10, 11, 12, 13, 14, and 15. You might think, if it's base 16, why don't we write up to 16? Well, actually, because we're including the number 0, between 0 and 15, there are 16 values. What we'll do here is, as soon as we get to 10, is that instead of writing down in hexadecimal, so 0 to 9 is the same as denary, as soon as we get to 10, to avoid us having to use 2 digits, we write the letter A. And then 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Okay, well, why don't we apply that logic here? So we can see that we have 3 lots of 16, so I'll write that out here. So we've got 3 times 16, great, but plus E lots of 1. In this context, can we see what E is going to be? If we consult our table here, we can see that E is 14. If you're ever in a situation where you're not too sure what they are, always remember A is 10, and then you can work up that B is 11, C is 12, D is 13, and E is 14. So to do our calculation, we'll say 3 times 16, so that would be 48, plus E, which is 14 times by 1, so that will be 14. So to convert that to denary is 48 plus 14, which I believe is 58, plus 4, 62 would be the answer. And our next question here is asking us to work on binary arithmetic. We're very familiar with how to add up questions in denary, so that's our number system we've learned to do since we were, 5, 6 years old. But this is saying, can we learn how to apply it to binary arithmetic? Let me just do a quick recap about how that's going to work. So let's look at a couple of examples using a nibble. If you remember, that's 4 bits. So we've got 0, 0, 1, 0, and then 0, 1, 1, 1. Okay, let's look at how this is going to work. If we start on the right hand side, because we'll do the same as we say the same as denary. So why don't I show an example here? 723 plus 879. This is a really good place to start, because if you follow the rules of this, it's actually the same for binary arithmetic. So I want you to think it through. Where do we start? Do we start on the right if we're adding it together, or start on the left? We start on the right. So we go 3 plus 9. Now that will be 12. But do we write the number 12 down? No, we don't, because the largest number you can hold is actually 9. As soon as you get to 10, you know what you do is that you actually remove the 1. Oops, I didn't mean to do that. And you what's called carry. So we'll write a 1 down here, and you've carried it along. Then you got 7 plus 2 plus 1, so that would be 10. Again, you wouldn't write 10 here. You'd write down 0, carry the 1, because you're carrying that 1 over. Now I want you to notice the 1 here doesn't actually represent 1, it's actually 10 from the previous column. 8 plus 7 is 15, plus 1 is 16. Again, you won't down 16, you write down 6, carry the 1, and again this 1 here, it represents 10, not 1. Right, let's apply that logic to binary arithmetic. Do we start on the right or do we start on the left? We do the same as we did with denary arithmetic. So 0 plus 1 is going to give us the answer 1. Now 1 plus 1 is going to give us the answer 2. Now in the same way we didn't write down 12 here, because you can only go up to 9, you can't write the number 2 here, because you can only have 0 or 1 as binary. So as soon as we get to 2, we carry that 2 over by writing a 1, because it's base 2. Every time you get to 2, you write 1 to signify it's 1 in the next column. Maybe this will help clarify it. We've got 1, 2, 4, and 8. Right, those are our units. Actually, 2 and this 1 and 1 is actually 2 lots of 2. So that's actually 4. And if we put 1 here, we can see we've got 1 lot of 4. Anyway, 0, 1, and then leaving us with, in this case, the value of 0, because we've taken it all across. 0, 1, and 1. Now, again, that would actually give us the value of 2. But in this context, we're not going to keep 2, are we? We're going to carry the 2 over by putting a 1 here. So the 1 actually represents 2. And because we've carried it all over, it's going to leave us with 0 in the column. Fantastic. And then we've got 0, 0, and 1, so finally it's 1. And you can actually check to see whether this was answered correctly. This first value you can see is actually just 2. This value is 4 plus 2 plus 1 is 7. 2 plus 7 should give you 9. And you can see in your answer you've got 8 and 1, you've got 9. There's one final example, which is we'll do in a second. So let's say we do 0, 1, 1, 1, 1, 0, 1, 1. Okay. Let's apply the logic we were just doing to this example here. 1 and 1, it would be 2. So you remember the way we dealt with that is we wrote down 0 and carried it over here with a 1. Now we've got 1 plus 1 plus 1. So that should give us the answer of 3. Now we know there are only 0 and 1 in binary. So in this answer, we definitely can't keep 3. When we put a 1 over to carry, are we carrying all of this, or are we carrying 2 of it over? We're carrying 2 of it over. So we have 3, take away the 2, leaving us with the answer in this case, which would be 1. 1, 0, and 1, it's going to give us 2. So we write down 0, carry the 1, 0, 1, 1, give us 2, so 0, carry the 1. And this is a bit of thing to notice here, is because we've got no way of storing this, we will call this what's referred to as a overflow error. Because unless we catch it, then we're going to get the wrong result, because that number there is 2, and it's saying if 7 plus 11 is going to give us 2, which we know is not right. Now, it's worth thinking how we might want to solve this kind of a problem, and actually the solution is quite straightforward. With an overflow error, to make it work correctly, what we'd have to do is introduce an additional bit here so that we can actually store the value. So that's the solution for it. Okay, why don't we try and actually apply this knowledge to the question here. So add together the following two 8-bit binary numbers, so these two, and express your response in 8-bit binary form. So it's indicating that if there is an overflow, it will just fall off the edge potentially. Right, I'm going to zoom in, and then we're going to have a good go at answering these questions. Okay, fantastic. So remember, do we start on the right or do we start on the left? We start on the right. 0 and 0, well, it's going to start off quite nicely because that's going to be the answer 0. 1 plus 1, well, that would be 2. Can we write down 2? No, we can't. We carry 1 over and we store 0. Because the carrying the 1 over, if you remember, signifies that we're actually carrying 2. Since we carry 2 over, it leaves us with a 0. 1 and 1 is going to give us 2 again. What do we do with 2? We write down 0 and carry it over. 1, 0, and 1 is going to give us 2 again. How do we deal with that? We write down 0 and carry it over. 0, 1, and 1 is going to give us 2. How do we deal with that? We write down 0 and carry it over. It's a bit of a repetition here. 1, 0, and 1. So we've got 1 and 0 and 1. So that's going to give us 2. How do we deal with that? We write down 0 and carry the 2 over, writing a 1. 1, 0, and 1 is going to give us 2. How do we deal with that? We write down 0 and carry the 1. A bit of a pattern here. And then finally, 0, 1, and 1 is going to give us 2. How do we deal with that? We write down 0 and carry the 1. Now, you remember, that's going to be something significant. What was it again? This is a overflow error. Fantastic. So the answer for this one is actually going to be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So it's basically saying add these numbers together. What did you get? You got 0. We didn't actually get 0. We actually got the answer would be 256. Identify the problem this addition has created. What was the problem? An overflow error. Now this time it hasn't asked us how to solve it, but how to solve it is we'd add an additional bit. So these questions are mainly on logical shifts, but it starts off with a conversion of a binary number into a denary. Previously we did denary into binary, so now we need to do it the other way around. The way we answer this question is very similar as we did before, is that we'd write the units in here. We can see that there are 8 bits, so 2, 4, 6, 8, so 8 bits, so I have to write the units for 8 binary bits. Once I've written the units out like this, underneath each of them, I'm going to write the binary value here. So I'm going to go from left to right. 1, 1, 0, 0, 1, 0, 1, 1. My apologies for my 8. That actually should be an 8 there. How do we do it now? Well, everywhere there's a 1, that means we have that value. So our answer would be 128 plus 64 plus 8 plus 2 plus 1. So 2 plus 8 is 10, plus 8, 18, plus 4, 22, plus 1, 23. So we've got 3, and then we're going to carry the 2. 2 plus 6 is going to give us 8, plus 2 is going to give us 10. So that's 0, carry the 1. So our final answer will be 203. Let's move on to the next question, and it's about logical shifts. Complete a 2-place shift to the right on the binary number here. Let me do a couple of examples of shifts, because actually they're not as complicated as you might think they are. So let's start off with a nibble like we did before. So that's 1, 2, 4, and 8. And then let's just plug in a number. 0, 0, 1, 0. Okay, so that's going to be a denary value of 2, right? So let's say this. Let's logical shift 1 left. Logical shift. What's going to happen? Well, we're going to take all these values here and write them 1 to the left. So down here, I'm going to write down 0, and then I'm going to write down 1, and then 0, and then 0, like I did before. 1, 0, 0. Now, this 0 has just, what was it when it fell off this side? It's an overflow. So we can actually, we're going to lose that data unless we have additional bits, so we can't deal with it. Here we have a blank value, and when it's blank, what you do is you pad with a 0. Okay, so moving it 1 to the left, what happened? Well, a 2 turned into a 4. Now what's the relationship there? Well, why don't we go left again? So now we've gone, we'll go a 1 left again, so this will be 2 left from the original. We'll write out the number again, so it will be 0, 0, 1, 0. Again, this value here has fallen off the edge. It has overflowed. And then the original spot we'll need to fill in now, and we'll pad with a 0. So now it's become 8. So 2, shift 1 to the left became 4, shift again to the left became 8. What's happening every single time? Every time you shift 1 to the left, it doubles the value. Shift 2 times to the left, you've gone, in fact, this might be a nice way of thinking about it. 1 to the left is 2 to the power of 1, so that's 2. Shift 2 to the left, 2 to the power of 2, so that's 4. Times it by 4. 3 to the left, 2 to the power of 3, so that'd be times 8. 4 to the left, 2 to the power of 4, so that's 16. So it's just doubling every single time. If you go to the right, if you can go to the right, so let's come up with another example down in here. So let's say we had 0, 1, 1, 0, and I did it, let's say 2 to the right. If every single time we go 1 to the left, it doubles, every time we go 1 to the right, it halves, so it divides by 2. So if you go once to the right, you divide it by 2, or halve it. If you go 2 to the right, you divide it by 4, or half of a half, or a quarter of it. So this value here is 2 plus 4, right? Because if we're doing units, it'll be 6. If we go 1 to the right, it becomes 3. If it becomes 2 to the right, it should become 1.5. Well, let's test it out, shall we? So if we're going 2 to the right, this will move down to here, this will move down to here, and 1 and 0 is going to kind of fall off the edge. So let's do that. 0, 1, 1, 0. These two are falling off the right edge. If you fall off the left edge, it's called an overflow. If you fall off the right edge, it's called an underflow. So these are two being lost. And we pad again, like we did last time, with zeros. So if we'd have shifted it 1 to the right, it would have gone from 6 to 3, which is halving it. 2 to the right should be 1.5, but because we haven't got any halves or quarters, it's become 1. All right, let's try out the question now then. So in here it says, complete a 2-place shift to the right on the binary number of this. So we can write out the original number. So 1, 1. In fact, let me write it out a bit nicer than this, a bit more spaced out. 1, 1, 0, 0, 1, 0, 1, 1. 2 to the right means that we need to shift all of these. So this will be down here, this will be down here. So this, 2 to the right, that 2 to the right. So I'd write it down here and write it on a different color. 1, 1. You see, that's moved 2 to the right, that's moved 2 to the right, and we just want to write out the whole thing like that. 0, 0, 1, 0, 1, 1. So these two here have underflowed, and here we'd have to pad with zeros. So what we'll do is we'll have to do that now to get the number. So this would pad with the zeros, and because these have fallen off the edge, they've underflowed, then we'd actually remove them. So the answer would be, the answer in green, let me just highlight, in fact, if I highlight that in blue, yeah, it's this one here. This is the answer. Okay? Explain the effect of performing a 2-place shift to the right on the binary number here. So we have to explain what's going to happen if we move 2 to the right. Now, if you remember, going it 1 to the right is dividing it by 2. So 2 to the right, dividing it by 4. 3 to the right, dividing it by 8. So in this case, we've gone 1 to the right, so it divides the value by 4. So the first thing is it divides the value by 4, but if you remember, these things fell off the side, so it's not actually going to give the right answer. So because it underflows, then we've lost precision. So, however, there is an underflow, so these numbers fall off the edge, so we won't get the right answer at the end. It'll be close, but not quite right, so precision has been lost. So maybe you could even refer to it as accuracy, potentially. Great stuff. So far, what we've looked at is how we can store numbers in binary. So denary numbers in binary, hexadecimal in binary. In this case, we're also looking how we can represent characters, so the letters we care about. One of the forms of character sets we can use is something called ASCII, American Standard Code Information Interchange. And what it does is it has a value, a number, which will be stored in binary actually, although this is a denary value, that represents each individual letter. In 7-bit ASCII, you can have 128 characters, including the break. And in extended ASCII, you can have 8 bits worth of it, which allows you to do things like accents. Now, the weakness, of course, with ASCII is that you can only really use sort of European-based languages, such as English. If you wanted to use, say, Chinese, you can't use ASCII. And if you remember, what you can make use of is Unicode. In this example, we've got examples of these letters, or the characters, and what they represent it. And the question is, how can the word mop be represented by using the ASCII codes? The first things we're going to want to say is we're going to say that each character is represented with an ASCII code. Each character is represented with its own code, and then what we'd want to do is we'd want to give an example of how to get mop. So you'd say that M would be represented by 77, etc. So for mop, this would be 77, 79, and 80. It's also worth pointing out that actually in the computer it won't be stored as 77, 78, and 79. You would also need to be able to find out what that is in binary, because that's how it actually would be storing it. Okay, let's start doing some definitions. A question like this is almost meant, I feel, to trip you up, because state what is meant by a character set. You might say, oh, a set of characters, for instance. But if you look at it, you should never actually you should never use the words inside the question in your answer. And somebody might think, well, you're just rearranging those words. So you have to be really clear with the definition here. So I would say something along the lines of all the characters that can be represented inside the set. Because it will depend on whether it's Unicode or ASCII, for instance. Okay, ASCII, so that's extended ASCII in this case, has 8 bits per character. Standard ASCII has 7 bits. Identify the maximum number of characters that ASCII can represent. So this is asking how many different values can you store in a byte. And that can go from 8 zeros to 8 ones, so from the value 0 to 255, so that would be 256 values. Great. Now it's asking you to use that knowledge to estimate sizes of files. So in this case it says, a text file uses the ASCII character set, which you've been told is 8 bits, so it's using extended ASCII. The text file has 2,000 characters in it. Calculate an estimate of the file size of the text file in kilobytes. So notice how it's just moved from bits to bytes. Now if you remember, how many bits were in a byte? That's right, 8 bits in a byte. So every character is 1 byte. So if there's 2,000 characters, and each character uses 8 bits, then what you can say is that that's actually the same as 2,000 times by 1 byte, which is the same as 2,000 bytes, and now it's asking for it in kilobytes, so that would be 2 KB in this context. For the next one here, it's saying that the ASCII character for J is 75. In the next question, it's saying write the 8-bit number of the character J. Now over here, you can see that J is actually 74. So let me write that over here. J equals 74 in denary. Now bear in mind what we want to do now is turn into 8-bit binary. Now we did it previously, so what we would want to do is write the units. So we'd have to write the units across here in binary for base 2. And then as we're going along, we'd want to try and turn 74 into it. So we say, can you fit 128 into 74? Answer, no, so that'd be 0. Can you put 64 into 74? Absolutely you can. So that would give you 74, take away 64, which is going to give you 10. And now we're doing something a bit straightforward. 32 into 10, that would be a 0. 16 into 10, that would be a 0. 8 into 10, absolutely. 10 take away 8 is going to leave you a 2. So no, yes, no. So that's it in there. Now the next question, it's saying turn K into hexadecimal. Well, first of all, we need to know what the ASCII for K is. We've not been told that. But something that's worth knowing is that all the characters are stored in order. So we can just write them in alphabetical order. So maybe start at H and then I, J, K, L, etc. If J is 74, K would be 75, L would be 76. We don't need to do the rest of these, but just worth knowing, I will be 73, H will be 72, and that's something you can just use. So once you've told one character, you can figure out the rest. So K, we can see is 75. So the question now is, can we turn 75 into hexadecimal? So if K is equal to 75, we need to turn it into hexadecimal. And so what we should do is you should do the unit. But remember now, because it's hexadecimal or base 16, it'll be lots of 1s and 16s. First question then isn't can 16 fit into 75, it's how many 16s can you put into 75? Well, 5 16s is 80, so that's too far. So it would be 4 16s. And then we'd have to account for how much we've poured in. So it would be 75, take away how many we've put in. Well, 4 16s is 64, so it'll be 75, take away 64, leaving you with 11. And so in here, we could write down 11, but if you're thinking, that doesn't seem right, you're quite correct. A is B, 10 is A, so 11 would be B. So the answer for this one wouldn't be 411, it would be 4B, because 11 becomes B in this context. So we've looked now how characters can be represented in binary and how numbers can be. Of course, everything in a computer must be stored in binary. That's your videos, that's your sound, your computer games, all in 1s and 0s. And the next thing we're going to look at is how images are stored in binary. So let's have a little read through here. It says, Layla is an artist. She draws images by hand. The image is then scanned and stored on a computer. This table has 4 statements. So let's consider how it actually is stored in a computer. Let's give a little example here. Excuse my poor drawing. Here's my beautiful image, and it's what's called a bitmap image, because what we've done is we've broken these down into individual pixels, and each of these pixels has one of 3 colors. Green, so that's my ground, blue is my sky, and yellow, which is my sun. What we'd have to do, though, to store it is that the computer doesn't know what blue, green, or yellow is. We'd have to define what these things are. So we'd have to define what 1s and 0s are for yellow, green, and blue. Now, if we just had the 2 colors, so let's say we just had yellow and we had, blue rather, and yellow, we could say that for blue, it could be represented by a 0, and for yellow, represented by a 1. Now, of course, we don't have that. We actually have a 3rd color, green. And so because we can only have 2 bits, we'll have to expand the number of bits. So maybe we say 0, 0 is blue, 0, 1 is yellow, and then 1, 0 could be green. And actually in the future, if we wanted another color, we could do 1, 1, which could be, I don't know, red or something. Okay, great. And then to represent the one we just did, let's just look at, say, this first row here and how we store it. Well, in the computer, it would read it as 0, 1, representing the yellow. What would the next thing be? Well, the next thing would be blue, and as you can see here, blue would be 0, 0, and then 0, 0, and then 0, 0. And so there's 2 main ways we can improve the quality of this image. We could actually have more pixels, So that would be increasing the resolution, so that'll make it sharper. And the other thing we can do is include more colors, but then that will require more bits. That's what's called increasing the color depth. The current color depth is 2 bits. Why is it 2 bits? Because we're having to use 2 bits here. We could have up to 4 colors. If we had 8 different colors, we would be using 3 bits. If we had 4-bit color depth, we could have 16 colors. 8-bit color depth, which is for GIFs or GIFs, depending how you call it, uses 256 colors, and on and on. So the 2 ways we can influence the quality of an image is increasing its resolution, so by using more pixels, and by increasing the color depth, we're using more colors. Downside is that the files will become larger. Let's use this knowledge then to go through these questions. The table has 4 statements about the storage of an image on a computer, so a bitmap image like we've just talked about. Okay. Tick 1 box in each row to identify if the statement is true or false. So each color has a unique binary code. By unique, it means nothing else can have the same one. And you can see here, blue is 0, 0. If another one had 0, 0, then how would we be able to figure out which is which? So each of these codes must be unique to the particular color. So that would be true. It is unique. Metadata, so that's some additional data, stores the color of each pixel in the image. Now, metadata are things like the size of a file potentially, the date it was modified, what the resolution potentially is of it, information like that. But the color of actually each pixel would not be inside the metadata, so that will be excluded. Bitmap is made of pixels. That's exactly right. You see here, it's just formed out of individual pixels. Now that might look blocky to you, but of course when you increase the resolution, the pixels become so small you can barely see them. So yeah, a bitmap is made of pixels. The higher the color depth, so the more colors, the smaller the number of different colors. So the higher the color depth, the more colors we can have. So that statement is false. Brilliant. Let's keep going. Layla stores her image on a secondary storage device, so maybe magnetic storage or flash storage or optical storage. Each image has a fixed size of 1 MB, so that's 1 megabyte or 1 million bytes. The storage device has a capacity of 3 gigabytes, so that's 3 billion bytes. Or in this case, 3,000 megabytes would be 3 gigabytes. Calculate how many images can be saved on the storage device. Show you're working. Okie dokie. So what we can say is that 1 GB, so 1 gigabyte, let me work on my handwriting. 1 gigabyte is equal to 1,000 megabytes. If you've got 3 gigabytes, then that equals 3,000 megabytes. Each image is 1 megabyte, so you can say it can store 3,000 images. Okay, so now we're looking about how the ones and zeros in your computer, those binary bits, how can they store audio or how can they store sound? I think it's worth taking a step back for a moment to consider how we think about sound in the real world or in the analog world. So I'm going to have another go at trying to do a drawing. In the real world, sound is a wave. Right now I'm recording this onto a microphone. That microphone is vibrating in reaction to the way that I'm speaking, and those vibrations are being recorded as a wave, but then it has to be turned into ones and zeros. How does it do that? Well, there's 2 different things. There's something we can do which is called sampling. So essentially it looks at the level of a wave and then records what level that's at. On our axis of our diagram here, on the y-axis, we'd have something called bit depth. What does that mean? Well, that's how many zeros and ones we're going to use to record it. So maybe in this case, we'll have, let's say we'll have 8 different values. We have 0, 0, 0. Maybe I'll zoom in, make it a bit easier for me to see. 0, 0, 1, 0, 1, 0, 0, 1, 1, 100, 101, 110, and finally 111. So it can be one of 8 different amplitudes or heights. So that's one part of it. What's the other part? Well, the other part is that we've got something called sample rate. So sample rate would be on the x-axis, and sample rate is how often we test it, and it's measured in hertz. 1 hertz meaning it would be sampling it once a second, 5 hertz meaning it would be sampling that at 5 times a second. So maybe in this case we can say that this is all in, I don't know, this is 1 second, this is 2 seconds, and so what we're doing is we're sampling it here, and then we're sampling it maybe again here, and then we're sampling it again maybe here and here, and I guess we must have done it at the beginning here. I'm recording basically what the height is at all these different points as we're going along. So this is going to be maybe 001, then this is going to be sampled, and maybe it's hard to say, maybe 100. This one is at 110. This is being sampled 011, etc. And as you go along, the more often you sample it, or the higher the sample rate, the higher the quality. And the more bit depth, the more bits you have, the higher the quality. The sample rate for something like a CD, I think it's 44.1 kilohertz, so it's being sampled 44,100 times in a second. And the bit rate is 16 bits, so every single time it's sampling, it's going to use 2 bytes worth of data. Right, that's how it works. So now let's come back to the actual question we were trying to answer. It says, describe what happens when the computer converts the music into a file. So how do we take this analog wave and turn it into a digital binary result? So to start off, I'd say that the height of the wave is going to be sampled and then recorded. So the height of the wave is sampled at regular intervals. What's it sampled into? Well, then this is going to be turned into binary bits. How many bits and how often that's sampled will be determined by its bit rate and sample rate. And that would be in hertz. Fantastic. Let's keep going. The sample rate is increased on the computer when recording the guitar, because presumably they want a high quality recording. Give 2 effects will this have on the recording? Okay, great. So the first and obvious thing to say is that, as you can see over here, sampling it more frequently will mean you can record the height of the wave more accurately. Well, what the big picture of that is, what's it going to do? Well, it's going to increase the quality. Are there any downsides? Well, I'm afraid there is. If you double the sample rate, you'll literally double the file size. So unfortunately, the downside is that it's going to increase the file size. Okay, great stuff. Let's keep going. Here we go. Here are a bunch of different questions now applying to sound, and we've got to figure out which one do we think is true or not true. So let's have a look. I've copied over our little diagram before so we can recognize what we're talking about. The sample rate is the number of times the amplitude is recorded per second, or amplitude is another word for the height of it. Does it do that? Yes, it does. So that's a true statement, because you see that is how often it's going to sample it. The higher the sample rate in hertz, the more times per second. The smaller the bit depth, the smaller the range of sounds that will be recorded. So in here, this is the bit depth. If you had 4-bit dip rate, you could store 16 values. If you have 3-bit, you've got 8. So it does. This is absolutely true. So the smaller the bit depth, the smaller the range of sounds. The larger the sample rate, the larger the bit depth. Ah, good. So these have nothing to do with each other, right? So you could have 10,000 sample rate and 1 bit depth. So they don't have anything to do with each other. So you can say false. They don't relate. The frequency and the pitch of the sound wave are measured. Not true. You're just sampling the amplitude or the height. So that's false. the sound is stored using pixels. It's trying to trip you up here. If you remember, pixels were used when you used images. So this is also false. This question here is a bit of a repeat from what we had earlier, but you're welcome to do it again. Kofi uses his computer to record an audio file of himself playing his guitar. Outline what happens when the computer converts it. So what was stage number one? Stage number one is that the height of the wave, or the amplitude of the wave, is measured, or sampled we called it, and then at set intervals or at regular times, and then this is turned into binary bits. So we can write that up again. Great stuff. And then the next one says Kofi increases the sample rate his computer is using to record his guitar. Explain two effects that will have on Kofi's recording. I think this is pretty much a carbon copy from before. The difference this time, though, is that it's giving 2 marks for each. So last time we said that the quality increases and the file size increases. That's not going to get you 4 marks. You're going to have to say why. So you can give the first one is that, yeah, the quality is going to increase. But why is it more? Why will it increase? Well, because as you sample it more frequently, what you're trying to do, the name of the game essentially is trying to make it so that the original sound file is as close as possible. You might have heard music, or potentially, like for instance, a phone call. When people talk on a phone, they don't sound exactly as they do in real life. And that's because the sample rate, and potentially also the quality of the microphone, etc., is not as good as reality. So the quality will increase. Why? Because it's going to get closer to the, or more accurate to the original. So the quality will increase because the sound wave is a closer match to the original. So that's how we get our full marks. Now, again, what's the other thing? Well, the file size will increase, but that will only get us 1 of the marks. The next mark will come from trying to explain why. Well, why? Because if you're sampling it more often, you have to store those bits. So you're going to have to say that because there are more samples, the file size will increase. So because there are more samples to store. It's worth pointing out that this would be exactly the same if bitrate increases. Bitrate increases, the quality will increase, and the sound wave will be a closer match to the original. And also the file size will increase because there'll be more bits required to restore all that extra bitrate. Okay then, we're on to the final topic, compression. So compression is when we've got a certain number of zeros and ones, and then we try to store it, but by using less zeros and ones. That's what it's all about. And there's 2 strategies we can use. One is lossless. So in lossless, you compress it, and so they're both about shrinking it. With lossless, when you decompress it, it's an exact match for the original. So if you started with 0, 1, 1, 1, 0, 1, that's what you'd end up with. With lossy, some data would be lost. So you would actually lose some data. So lossless, if you apply it to text, when you decompress it, you will have the exact match to the original text. If you use lossy compression, some data will be lost permanently. Hey, why don't we just always use lossless then, so we never lose any data? Here's the downside. For things like, say, 4K video or photographs, if we use lossless, the file size will be way larger. And actually, human beings often aren't actually able to notice these small differences. So with lossy, even though lots of data will be potentially lost with, say, a video encoding on Netflix, you aren't actually sensitive enough to notice it that much, and it's really worth the trade-off because the file size will be far smaller. In this case, Kofi uses his computer to record an audio file of himself playing his guitar. He emails his recording to a record label. Okay, so that gives the impression that we're going to kind of want it to be high quality, right? He uses lossy compression to produce the music file. Explain 2 reasons why lossy compression is beneficial. The first and main benefit of lossy was that it's going to allow you to reduce the file size substantially. And audio files can clearly be quite large, especially if you're using a high sample rate and bit rate like this, like Kofi is using. So actually reducing it substantially will make it easier to send and be stored, take up less space. Now, the downside, of course, with lossy compression is that some data will be lost. And if Kofi was sending a letter, or if he was sending an essay or something, he definitely wouldn't want to use lossy compression, because some letters might go missing or change to different characters. That would really be a bad idea, and you'd have to use lossless. But because it's audio, the stuff that's going to be removed, the audio that's going to be removed, might be things out of human hearing. They'll do things where you won't actually notice the difference. Now, you could actually make an argument for an audio file to go to a record label that it might be worth using lossless. Yes, it would be a bigger file size, but you might want as high as quality as possible. However, in this case, they've only asked you for the benefits of lossy, so that will be our answer here.